The Deutsch algorithm already nicely illustrates how a quantum computer can speed up the task of finding an answer to a mathematical question. But the question that it addresses is a relatively simple one, and that's mainly down to the simple functions that it can deal with. These functions have just a single bit as an input and a single bit as an output. In order to address more general questions, we have to increase the complexity of these functions. And we do this in several steps. First, we are going to consider functions that still have a single bit as an output, but the input can have many bits. And there we are going to look at two different algorithms, the Deutsch-Josza algorithm, which is just a generalization of the Deutsch algorithm, and the Grover algorithm. In the Deutsch-Josza algorithm, the type of functions are still somewhat constrained, but this constraint is removed in the Grover algorithm, which will make it immensely practically useful. Later on, we are also going to discuss functions that have many bits as an output, and in particular the quantum Fourier transform. And this will have many applications that we will then discuss. But let us start with functions for which the output is still a single bit, and therefore turn to the Deutsch-Josza algorithm. In the Deutsch-Josza algorithm, we have these functions f of x. So f is just one bit, and x can have n bits. And we are still interested in classifying them into constant and balanced functions. So for a constant function, f of x always takes the same value. So there are two different types. While for the balanced functions, f of x is 0 or 1 half of the time. So there are exactly two constant functions, but many more balanced functions. But this does not cover all possible functions, and in order to illustrate this, let us consider the case of 2 bits. So we have an input x, which has 2 bits. So these are the possible inputs. And now we have plenty of functions depending on the combinations of the outputs. For instance, the output could always be 0, and this is of course one example of a constant function, but it also could follow this pattern here, or this pattern, or this pattern, or this pattern, and then we can just continue. So I'm just going to write them all down, and here we have covered half of them, so there are still plenty to go. And I of course would not be able to remember all of them, but I think you already see the pattern that I've applied here. Because looking from the top, I just enumerated them as binary numbers, starting from 0 to 15. And therefore we could enumerate all these functions from f0 to f15. So there are 16 different functions. So our constant functions cover these two here, while the balanced functions are all those in which there are as many ones as well as zeros in the output. So 2 of each. And these are these. So we have 2 constant and 6 balanced functions, but also some functions that do not follow this pattern. So for the Deutsch-Josza algorithm, we assume that these do not appear. But once this is guaranteed, we can distinguish between the constant and balanced functions by a very similar strategy as in the Deutsch algorithm. And so we are going to base this again on the corresponding function gates. Now, as we are dealing with functions that have n bits as an input, we have an input here, which represents n of these bits. And so this line here actually carries n qubits. And this is indicated by this symbol here. And our output is just a single bit, so we just have one additional bit down here. And what we obtain at the other side is just the memory of our input. And here this will be transformed into this expression here. So the only difference is that our input is n bits. To implement the Deutsch-Josza algorithm, we are placing this function gate in between Hadamard gates. And in particular, this will involve Hadamard gates acting on all the individual quantum bits in the input. So all n of these, and I'm going to denote this by an h with a superscript n. So h with this superscript is the product of all the Hadamard gates acting on all the individual quantum bits in here. And we are going to start out with the state 0. So here this is still a line of n quantum bits. In particular, the state 0 really corresponds to zeros for all the individual quantum bits. So these are n entries here. Down here we also have a Hadamard gate, just acting on this individual quantum bit. And this we will again initialize in the state 1. And on the other side, we also place Hadamard gates here acting on all the quantum bits. So again, using this symbol here. And down here, this will again be something that we can do as we like, but it is useful to once more place a Hadamard gate here. Just as in the Deutsch algorithm, this is just for convenience. It is actually not too difficult to work out what happens next, because we have already established that applying all these Hadamard gates to this state here will just give us the state capital psi, which is the superposition of all the possible computational basis states that I here enumerate as x. So this means that at this point we have this state capital psi. And down here we have this superposition that we always use to mark states. So at this point we will have marked all these states, giving us a superposition of all the computational basis states. But with these factors here in front. And now we have to run this state through all the remaining Hadamard gates. So one Hadamard gate acting on each of the quantum bits. But for this we can rely on our preparations, because they tell us how these states x here become transformed into very specific superpositions of all the computational basis states. In there we have another factor of 1 over root curly n. So overall a factor of 1 over curly n in front of this. And then we have a double sum running over x and also z. So this will now be a sum over all the computational basis states z. And in front of this we have factors of -1 to the power f of x and -1 to the power of the bitwise product between x and z. So this is our final state for these quantum bits, and we will return to it very soon, but let's first establish what happens to the other quantum bit, the one down here. Well, this remains in this superposition through the marking of the states, and the Hadamard gate then just returns it back to its initial state. So doing measurements on this additional bit does not tell us anything about this function, just as was the case in the Deutsch algorithm. And let's therefore see what happens when we do measurements on all the other quantum bits described by this quantum state here. And specifically, let's ask the question, what is the probability to do such measurements and observe that all the quantum bits are 0, which means that z is 0 itself. And this is the square of the amplitude in front of the corresponding state. Well, if we place z equal to 0 here, we simply have this term here, so that would be 1 over curly n times the sum over all x of -1 to the power f of x. And now we see that this has two very specific outcomes. Namely, this will be 1 for a constant function, and it will be 0 for a balanced function. And we see this very directly because for a constant function, all of these numbers here are the same. So they add up to plus curly n or minus curly n. Then divided by curly n, we just get 1 or minus 1. And when we square this, we just obtain 1. And for a balanced function, we have just as many 1s as minus 1s in this sum here. And therefore, this sums to 0. And therefore, this first case here corresponds to a constant function. And the second case corresponds to a balanced function. And this means that we have everything in place. By embedding the function gate into the Deutsch-Josza algorithm as described, we arrive at a final state on which we can do measurements. And whenever we find an outcome where all the quantum bits are in the state 0, then we know that we have a constant function. While for any other output, we know that our function is balanced. So we have achieved this distinction with just one call to the corresponding function gate. And this is a significant speedup when we compare this to the classical case. In particular, when we are given a constant function, but we do not know this, and we want to verify that it is constant indeed, then we will have to call this function n over 2 plus 1 times. Because otherwise we cannot be sure that we are not dealing with a balanced function, for which just by chance we picked n over 2 inputs, for which all the outputs are the same. So this is very different from the Deutsch-Josza algorithm, where we always need to call this function gate here exactly once. Nonetheless, we needed the guarantee that our functions are either constant or balanced. So let us turn to the Grover algorithm, where this constraint is being removed.